Welcome to this YouTube tutorial session. In this particular section, we are going to look at how to create a flood risk map of the Greater Accra region. But before we delve into the demonstration, we should know and understand what a flood risk map is and what goes into creating one. By definition, a flood risk map is a visual representation of an area that is highly prone to flooding during a heavy downpour. These maps use data on factors like elevation, slope, rainfall patterns, drainage networks, and soil types to predict flood risk zones. In turn, these maps become powerful tools for disaster preparedness, informed decision making, and risk mitigation strategies, among others. So, why Greater Region? The Greater Accra Region as a study area. Well, the Greater Accra Region has had a long history of floods and therefore faces a significant threat from flooding. Also, especially during the wet season or the rainy season, the Greater Accra Region receives a significant amount of rainfall. The next reason is also because of urbanization. Greater Accra is a highly urbanized space, which means that much of the natural landscape has been destroyed, paving way for grey infrastructure, and these grey infrastructure in turn become, these grey infrastructures are rather impervious surfaces. So from the little environmental science we did back in our elementary or basic science, we know that the natural landscape tends to mitigate natural disasters such as floods, by reducing runoff and the ability to absorb excess water. But with the case of urbanized space, with all the tarred roads, with all the buildings and other impervious surfaces, water cannot seep underground or cannot be absorbed, and they therefore accumulate at the surface of these places. And so over a period of time, especially if the rain lasts for an extended period of time, then the chances of flooding increases. Then finally, we chose Greater Accra Region because of the terrain. The Greater Accra Region is mainly a coastal plain which sits at the base of the Togo Range. So it's a low-lying, gently sloped area with a few areas of significant elevation, but all round the terrain is that of a flat, gentle surface. Now the factors, depending on what you have available. In this case, we had rainfall, land use, land cover, slope, digital elevation model, and then the proximity to streams. These are the factors we chose for this particular demonstration. The factors are not limited to this. You could have things like, you could consider things like soil type, that is if it is readily available. But then for this demonstration, we just have this 5. Yeah. Now, as you can see, there are scores attached to them, and these scores are arbitrary. But for an accurate analysis, it is advised you discuss with experts in this field who give you a much more realistic values or scores you can attach to the individual indicators. This will be, the reason why the scores are attached is because we're going to use the weighted sum analysis to generate our flood risk map. And so you can see over here, land use, land cover has the highest score of 0.3. Because due to the fact that the Greater Accra Region is the most urbanized space. It's one of the most urbanized spaces in the whole country. So I find it appropriate to attach or give the value of 0.3, which plays an important factor in whether or not an area is prone to flooding. And then the least score was given to the slope, but because generally speaking, the Greater Accra Region, like I said in the previous slide, is a coastal plain and it is gently sloped, no little or no. There are few bits here and there that have a significant elevation to it, but then generally speaking, it's a gentle. It has a gentle terrain. That's the word I'm looking for. Gentle terrain. Now, the workflow or this demo follows this methodology. So, with the main indicators being the slope, digital elevation model, the rainfall, land use, land cover, and then the proximity to stream would all go reclassification. The purpose of the reclassification is to make all of the factors or indicators unitless and then have a common scale or denominator, which will be 1 to 5, where 1 marks areas that are least prone to flooding and 5 marks areas that are the highest prone to flooding. And as you can see from the analysis, much of the work will be done with the digital elevation model. Some hydrological processes would have to be run. This is to simulate, first of all, to simulate water flow over the terrain of the Greater Accra, and then generate a stream network, which will be then used in calculating the distance to the stream channels in the Greater Accra region. They'll all be reclassified and then run through the weighted sum analysis. Now that we have the theoretical understanding of what we are going to do, we can jump in to the tutorial. I've gone ahead to load the ArcGIS professional software, and I've loaded the data we are going to use for the demonstration. We have the digital elevation model, the rainfall, land use, land cover, and what is left is the slope and the proximity to the stream channel. But the first one we're going to do is generate our slope. Like I said in the previous slide, much of the analysis will be done with our digital elevation model. So in creating your slope, the first thing we're going to do is locate our geoprocessing toolbox in the analysis tab, and then search for slope. So I'll select the option under the spatial analysis toolbox, click on it, and then the dialog box will pop up. So the parameters here, the input raster here would be our digital elevation model, and then the output raster would be the name. So Greater Accra _ slope. I'll leave the output. The output measurement will be in degree, and the method will be planar. The Z factor is 1, but if you want to increase it for a much more dramatic effect, you can do that. I'll leave the rest as default and hit run. So now we have our slope, which is measured in degrees. The output measurement is in degrees. So like I said, the slope describes generally the terrain, how smooth the terrain of the place is. So Accra is a coastal plain with an all-round gentle slope, and it sits at the base of the Equipem Togo range. Yeah, so much of the landscape of the Greater Accra region is gentle, with few areas of high elevations here, marked over here, and much of it over here at the southwestern part of the region. The next thing we're going to do is fill. Fill is an important step or procedure you have to follow, especially when you're performing hydrological analysis using the digital elevation model. Much of the, or most often or not, the digital elevation model comes with errors in the form of pits, which may affect in the long run, may affect the analysis of the work you are doing. So before we continue with any hydrological process, as shown in the methodology, we have to fill the digital elevation model. So I'll type in fill and then select the first one. So the input would be our digital elevation model, and the output surface raster, I'll give it a name DEM fill, let's go fill. This is where we would store, this is the name, and this is where we would store the output surface raster. I'll leave the limits as it is and then hit run. Now we've created our flow. The next thing we're going to do is simulate our flow direction. So we want to see how water would flow over the terrain of the Greater Accra Region, the coastal. We want to simulate how the water would flow over the terrain of the Greater Accra Region. So we would use the flow direction. Tool under the spatial analysis toolbox. Select this and then select the DEM we just filled, and then give it a name, flow direction. I'll just give it flow direction, which is straightforward. Leave the rest as default and hit run. Now the results shows cell values or pixel values, and the various colors show the direction of how water or any fluid or liquid or what have you would flow over the terrain of the Greater Accra Region. Now that we've generated this, now we can generate our flow accumulation. So I'll just add accumulation to this, and then click on this, and then our input raster would be our flow direction we just created, and then the name would give the raster we just created, the flow accumulation raster, and then leave the rest as default. Now the flow accumulation tool, what it does is that it generates a raster that shows areas that would accumulate when water flows. So areas that accumulate across the terrain, areas that would have high accumulation of water, or where accumulation will occur over the terrain or across the terrain of the Greater Accra Region. So I'll leave the rest as default and hit run. Okay. Now, once I zoom in, now we can see areas across the terrain that would have flow accumulation. So it's marked by it's marked by areas. Sorry, so apologies for this. It's marked by areas with that have white. So these are cells that are white, and so these are areas that have significant flow accumulation. Right over here. But then this will not be enough to generate a network of stream channels across the terrain or across the region of Greater Accra. We need to set a threshold of 500 that would select significant amount of streams that have values above 500, stream values that have values above 500 to generate a network of streams. So to do that, I'll go to my raster calculator, my geoprocessing search box. I'll search for raster calculator. So I'll select this one under the spatial analyst toolbox, and then the flow accumulation raster, I'll select that, and then add an operation which is greater than 500. So the output here would be flow accumulation raster. Just add an underscore raster. Once I'm done, then I'd hit run. So now the layer is in a binary form, 0 and 1. So 0 are gray areas, and 1 represents stream channels across the Greater Accra region that have significant flow accumulation greater than 500. So now we can generate our stream order, which would be used in the tool will be used in generating a hierarchy or network of streams across the Greater Accra region. So to do that, I'll just go back and then the search box, search for stream order. So I'll select this one under the spatial analyst tool, and then the stream input stream raster would be we'll use the flow accumulation raster we just generated, and then we use the flow direction raster too as well. So I'll change this to stream order, and then so this method is a very popular one in generating a stream, or the Strahler method. So I'll hit run. So once you zoom in, you can now see the levels or the hierarchy that it has generated. So we now have our stream network based on hierarchies. So from 1 to 6 that run across the Greater Accra region. So I'll zoom back to layer, and then now we can change this raster layer into a feature layer, and then generate or calculate our Euclidean distance or proximity to stream channel. So these are significant stream channels. Supposing these areas flag, which areas would be most affected per the stream channels we've just generated. So I'll zoom back to layer again. Zoom to layer. Okay, I made the stream order 1, so I'll just remove that and maintain this. Now I'll go back and then I'll use stream to feature tool. So the spatial analyst tool, select the first one. The stream raster is the stream order we just created, and then we use our flow direction raster tool as well. I'll give it an appropriate name. So I'll just make it stream feature and then hit run. So this is our stream feature. Now we can go ahead and calculate our Euclidean distance or analyze our proximity to the stream channels or stream network. So to do that, just go back and go to Euclidean, search for Euclidean distance, the first one. Take notice and pay attention. There are different options. There's Euclidean direction, Euclidean allocation, and Euclidean back direction, but we're looking for Euclidean distance. So we'll select this one and then input our raster. We'll use the stream feature and then we can give it a much more proper naming. So I'll just write proximity to channel. Over here, we'd have to set the parameters, otherwise the analysis will run out of the extent of the Greater Accra region. So for the coordinate system, I'll use that of the current map. And over here, I'll select the Greater Accra region, and then the mask tool as well. I'll select the Greater Accra region. Leave the rest as default. Sorry, let me go back. Leave the rest as default and hit run. So we've generated our Euclidean distance. Now that we have all our main indicators and factors, we can now reclassify them, meaning we would make them unitless, and then they would all have a common denominator, a common scale. And the scale we're going to use is 1 to 5, where 1 marks areas that are least prone to flooding, and then 5 marks areas that are at high risk of flooding. So I'd go back and then search for reclassify. Then select the reclassify under the spatial analyst tool. So the first input raster we are going to use is the digital elevation model, and we are going to use under the field we're going to reclassify is the value. So on the table here, I'll select classify, and then I'll use the natural breaks method, and we're using 5. I'll hit OK, and then this is where I would have to recode the values based on since we're using the digital elevation model, and the digital elevation model just describes it's used to first of all show the terrain and then depressions of an area, the highs and lows. So an area such as this implies that it is on a flat or generally flat surface. So flat areas in general are much more prone to flooding as compared to areas that have high elevation, which is marked by this region over here, 410. So logically, the 1 would be 5 based on the scale we're using. Sorry, 5. Then the 2 would be 4. And then 3 marking moderate chances of flooding. And then this would be 1. Sorry, 2. And then the last one would be 1. Marking areas of least chance of flooding because it's an area with a high elevation. So I'll just hit enter and then give it an appropriate name. So DEM underscore reclassify. Sorry. Yeah, so flat plains generally are much prone. We're using a bit of logic here. Flat areas are much prone to flooding compared to areas with high elevation. So least chance, highest chance. I'll hit run. And there we have it. So let me just uncheck the stream feature we created earlier so that we are not confused. So once you zoom in, let me uncheck some of them. I don't need a lot of them. Just uncheck this. And then, sorry. Yes, so the areas that are in brown patches are areas that have least chance of flood, meaning they are very high. They are very high points. So if I uncheck this, you can actually see that per the terrain or the topography of the area, you can actually see that these are high areas of high elevation. So it makes sense that such an area would have the least chance of flooding because if it rains, the rain usually flows, or the rain usually flows, water generally flows from a region of high elevation to a lower region. So from here to here, much of the runoff would be from the top and then accumulate at the bottom over here. So this is near Accra. So I'll check this again and then zoom to layer. Now the next one we are going to reclassify is our slope, the Greater Accra slope. We used the Greater Accra slope we used. So the reclass field again, the reclass field is the value. So I'll just select classify again, and then I'll use the natural breaks. So again, the slope generally follows the logic of the digital elevation model for obvious reasons. So coastal plains or low-lying places or a gentle terrain compared to an area that has a high elevation would flood because of the runoff coming from the top. So the runoff coming from a higher slope down to like a gentle slope will flood. So I'll hit OK, and then the same logic. So this to this is a low-lying or a gentle slope. So this would be 5, 4, 3 marking moderate, 2, and then 1. I'll hit enter, and then I'll change this to slope reclassify. So I'll hit run. So similar to the digital elevation model, once I zoom in, the areas that are a shade of say green yellowish, a combination of green and yellow over here, least chance of flooding, and then low, and then the blue, the shade of blue over here also least chance of flood. So once I check this, it's similar to that of the digital elevation model. And so let me uncheck the DEM, and you can see that yes, this place has a high slope compared to this one, which is low lying. It's a general space. So there you have it. So I'll zoom out, zoom to layer, and then reclassify our next data, which is the rainfall. So the rainfall, we would reclassify the value field again, and then select classify under here. We're going to maintain the natural breaks, and then hit OK. Now the rainfall starts from the least, which is 261, to the highest. So an area that receives much more rainfall is much more likely to flood as compared to an area that receives least amount of rainfall. So in comparison, this area would receive the amount of rainfall it receives in comparison to this area over here makes it like the chances are low compared to this area over here. So the coding over here makes sense. So 1, least or no chance of flooding, and then 5 has a high chance of flooding because of the amount of rainfall it receives. So I'll leave the code as is, and then go to the name and then make that rainfall. And then hit enter and then run. So as you can see, areas in yellow have at most chance of flooding, they experience more chance of flooding. So which is the southwest part of the Greater Accra Region. And then one over here actually have the least chance of flooding based on the amount of rainfall this area receives. So here, no chance, near chance of flooding. Over here, the yellow bit has a high chance of flooding.
So this is it for this particular session. In the next session, we'll look at reclassifying our land use and covered data, and then our proximity to channels. See you there.